So we were doing asymptotics, right? We have defined big O, big omega, theta, small o, small omega, O tilde and omega tilde. So this omega tilde was big omega tilde, and similarly you can also define small o tilde and small omega tilde. So points here, or maybe we do some small examples first. So if you look at the function n plus n square times 100, okay, n is the formal variable. Think of it as input size. So if you have a algorithm that has this much time, so this we can write as big O of n square simply, right? Because 100 is a constant factor, we can drop it, and then in n and n square dominates. So you can actually say that the whole thing is kind of n square. So that is what big O of n square signifies. But we can also say that this is actually big omega n square, right? Because it is not only upper bounded by a multiple of n square, it is also lower bounded by a multiple of n square. So ultimately it is actually theta n square. It is all three. And it is also small o, let us say of n to the 2.01, right? Because n plus n square will be smaller than n raised to 2 point something. So you can put 0.001, 0.01, 0.1. So LHS left hand side will be strictly smaller than this, right? In the limit of the ratio is 0. On the other hand, it is strictly bigger than n square by log n. Right? N square by log n is strictly smaller than n square. So n plus n 100 times n plus n square is actually strictly bigger than this. Okay, another example is which you will often see, n log n. So what is n log n? N log n is upper bounded by, let us say, this power n to the 1.01, right? N log n is almost a linear function. So anything n to the 1 plus epsilon, that will be larger. And in fact, it is small o of n to the 1 plus epsilon for any positive real number epsilon. In the limit, because log n by n to the epsilon tends to 0. Okay, that is important to remember. So log n is exponentially smaller than any polynomial in n. So in general, you should remember that n to the c is always smaller than 2 raised to n for all constant c. Okay, polynomial is always smaller than exponential. This is what we are saying here. This asymptotics you should always remember. This is important. Okay, some more remarks. So as mentioned before, the input output tape is only for writing the output string. Okay, you are not allowed to do anything else on the I/O tape. For all the other stuff, use the work tape. And sometimes you may not even need to write the output. You can also just place it on the work tape if it is small enough, especially if it's a decision problem. Okay, a second important remark is that you know this binary search algorithm, right? So is binary search really log in time? So in terms of Turing machine, it cannot be. So you can search a name in a directory in login steps. In fact, quote unquote login steps. But this is actually not possible on the tape, right? Because on the tape, your head can only move one cell at a time, one cell to the neighboring, one of the neighboring cells. So it cannot really jump from one end to the midpoint of the input. Okay, that jump is not possible. So that jump will actually already take n/2 steps. So so this login step algorithm, which you keep seeing in binary search, this is actually not in the Turing model. Okay, there you assume random access, and Turing machine does not have random access. So it doesn't mean login time. Okay, this is not the time complexity in terms of Turing machine. Why? Because you need to assume indexing and random access. Which requires n to be fixed or constant. Okay, so this actually works in directories well, because directories are finite length strings, right? Directory will only have names, and names are finite. Directories cannot be infinite, really. So that is why saying login there makes sense. But and also you have to jump. You have to jump from endpoints to the midpoint, and so on recursively. Neither of those things are possible in Turing machine. In Turing machine, it will really be n steps, order n steps, going from endpoint to midpoint. Moreover, indexing is not possible. I mean, you cannot just number the cells and say that I directly jump to cell I. Okay, so those things actually are only possible when n is constant. And n is not constant in Turing machine. This input size is assumed to be arbitrary, at least when we talk about time complexity. Okay, so this might be a common confusion when you try to do binary search in the Turing model. So if you, in any algorithm where you need to look at a long input, you will have to scan it. It will be at least linear time. So once we have gone through the definition of Turing machine, a definition of problems, Turing machine, time complexity, asymptotics, now we can talk about what can be simulated on a Turing machine. So the Church-Turing thesis comes into the picture. And what does it say? So it says that everything can be simulated on a Turing machine. So every realizable computing device okay, so it could be transistor based in the old days, or now silicon based, or in the future DNA based or neuron based, like our neuron cells, or in the future quantum based. Or any, even for now, alien technology. Everything can be simulated by or simulated on Turing machine. Okay, this is the thesis. Obviously, you cannot prove it. You can only disprove it, and to date, in the last 1 century, it has never been disproved. Okay, so whatever computing device is invented or thought of, they are all simulable on a Turing machine. Okay, so in this sense, Turing machine is the universal machine, can simulate anything. So the problems which a Turing machine solves, they are called what? They are called computable. Decidable or recursive. Okay, these terms mean the same thing. So a problem is computable if it can be solved on a Turing machine by an algorithm, and a problem is decidable or a problem is recursive if there is a Turing machine for it. Now there is another term which is more general than recursive. It's recursively enumerable. So recursively enumerable is a more general concept. Okay, just I wanted to note that enumerable, when we say, it's a different term. So recursively, there are recursively enumerable problems which may not be recursive, which may not have a Turing machine and algorithm. Okay, so enumerable just means that there is a Turing machine which can output the yes strings, like keep printing the yes strings. In some order, all the yes strings will be printed. Okay, but that somehow is not the same thing as computability. Okay, in computability, you will be given the Turing machine will be given an input, and then the Turing machine has to halt and say yes or no, yes string or no string. So I will not go into this because this is already covered in theory of computation a lot. But Yeah, the most general thing you can think of is recursively enumerable, and recursive is more special. And what is more special, which we study in this course, is efficiently solvable problems. Okay, so what are they? So function f we will call polynomial time computable. Okay, polynomial time computable, not just computable, but computable how fast? So polynomial time. That's the time complexity. And obviously you can define it as if there exists Turing machine M for f with time complexity Tn, and Tn has to be a poly function, polynomial in n, so n to the c. Okay, where c is an absolute constant. What does constant term means? Constant means doesn't depend on n, on the input size. Okay, so that is independent of the input size n. This is what we will always mean. Okay, constant variable will be n input size, because you want to study all possible inputs, and constant will be something that doesn't change with n. Okay, so c is a constant. It's actually a universal constant. Think of c as 10, and functions which have a Turing machine that halts in this much time, n to the c time at most, those functions, those problems are called polynomial time computable. So we'll usually shorten it to poly time, and informally we can call these Turing machines efficient algorithms. So informally we call such f, or maybe we call such Turing machines or algorithms efficient algorithms. Okay, so almost always efficiency or efficient algorithm will mean Turing machines with time complexity a polynomial. Even if it is n to the 100, we are calling it efficient, because as remarked before, n to the 100 is smaller than 2 raised to n. Okay, so 2 raised to n we call inefficient, and n raised to c we call efficient. So let me give you an exercise. So any C program okay, you write, if you are looking at a C program that is efficient, its time complexity is polynomial in the input size, any efficient C program can be written as an efficient Turing machine. And conversely, any efficient Turing machine or algorithm can be converted into a C program, efficient C program. Okay, so just do this simple exercise just so that you understand the relationship between actual C programs and these abstract Turing machines or mathematical Turing machines. The reason why this efficiency translates is or captured by Turing machine is obviously Turing machine steps. Each step is so simple you can simulate it by a C program. And so if the steps are few in Turing machine, steps will be few in C program execution or any computer program execution. Converse is true because whatever C program will do or a computer program will do during execution on an input, it can be faithfully simulated by Turing machine steps. So the Turing machine will also have few steps. Okay, just convince yourself about this. So what this means is this is kind of an efficient version or variant of Church-Turing thesis, if you will, that all these realistic computations which are fast, they are fast because the Turing machine implementations are also fast. So thus, if a problem is hard for Turing machines, then it is also hard in real life. Right. So that is why Turing machines are so popular amongst theoreticians, because if we show that some problem is very hard for Turing machine, then it must be very hard also for, it will be very hard also for any kind of realistic computation. Now notice that Church-Turing thesis was a bit more general. It didn't talk about efficiency, it only talked about computability. So that has held true. Efficiency part in the future it may change, because for example it is known that if you can design quantum computers, then they can solve problems faster than existing computers. Okay, so let me just remark that this efficient, if you will, Church-Turing thesis might fail, or it will fail if you build a quantum computer. This is known. Okay, we will not do it in this course, but you can do it in quantum computation courses. Okay, so this is why there is a problem in efficient version of Church-Turing thesis, that it may not be true that any efficient problem can be solved on real computers. There might be some other architectures or physical devices which may solve a problem faster. Okay, for example, quantum computers could possibly solve let me call this might. So certain problems we believe are solvable faster on quantum computers than current computers. But remember that this is, we are only comparing efficiency. Computability is trivial. Okay, computable, the problem whether you solve it in this much time or much bigger time, computability is not concerned about that. Computability is only concerned about finite time. Right, so that Church-Turing thesis stands solid, but efficient version is not so powerful or so realistic. So can you feed a Turing machine to another Turing machine as input? Okay, which is like saying, can a C program take another C program as input? So of course yes, because compilers do that all the time. Compilers take as input, right? So let's do that here. So feed Turing machines to themselves. So how do we formalize that? It's not difficult, because Turing machine, remember, has finite control. So it's a finite string. You give that to another Turing machine as input. So Turing machine has finite description. Right, alphabet, state, transition function, or think of the state diagram. It's so completely finite. I mean, by definition, it is finite. So you can think of giving that picture to a Turing machine, right? So we can encode it as a Boolean string. Okay, so there might be many ways to encode. Let us fix one. So let us fix some encoding. So for example, one option is, first the gamma is presented in binary, then comma is put, and then Q is presented in binary, and then delta is, then comma is put, and then the transition function delta is put in binary. Right? So that's a string, and that represents a Turing machine, and you can give this to your algorithm or your Turing machine. Okay, so Turing machine taking a Turing machine, that is possible. And for a string alpha, we can write M alpha to be the Turing machine that string alpha represents. Now, since the encoding is fixed in some way, maybe not every string is a Turing machine, is describing a Turing machine. So if it doesn't, then you, in that case, you take the Turing machine M alpha to be just some trivial Turing machine. So okay, so let me define it in two ways. So M alpha is the Turing machine that alpha encodes. If alpha does encode, . Otherwise, the Turing machine computing the zero function. If alpha doesn't encode. Okay, so this is a definition by two cases. So either alpha does encode a Turing machine, then you just use that Turing machine as M alpha, M sub alpha. If alpha doesn't encode a Turing machine, then you take the zero Turing machine. So yeah, now strings correspond to Turing machines, and that is amazing, right? That any string can be seen as an algorithm. So every string is also an algorithm. Right? So you can think of strings as algorithms, algorithms as strings. If you think about it, when you write a C program, it is already a string, right? It's a string in your English language, for example. So just that idea, but abstracting it mathematically will be very helpful. So now you can see that there exists a universal Turing machine U that on input alpha x simulates M alpha on x. Okay, so now you can design a Turing machine called U, which will take another Turing machine with its input and then run that Turing machine on the given input and either halt given answer or doesn't halt. All that depends on what alpha was, right? So what is this Turing machine design? So this again is you can do it as a homework exercise. So you, let me just say it's a proof idea, not the formal proof. Formal proof you can write down. So U reads the transition function delta of M alpha and decides the next step. Here remember that U also has two tapes, input tape on which alpha comma x is written, and there is a work tape. So it can actually divide its own work tape into, I mean, you can use to simulate tapes for M alpha, right? So the only thing which is missing in alpha are these tapes, which M alpha would have had. They are missing because alpha is just a finite string. There is no infinite memory there. But memory U has two tapes. In fact, it has this work tape. So on the work tape, it can simulate whatever M alpha wants to do. Right? It can, in fact, in the worst case, it can divide its own. U can divide its own work tape into an input part and a work tape part, and whatever M alpha says, it can simulate that. So do that, as complete this proof as homework exercise. See whether what the time complexity of U is. Is it as good as M alpha? Is it much worse? And just with this definition and this observation, now you can show that halting problem is terribly hard. So this problem is the following language, halt, right? Or let me use capital to avoid confusion. So halt is the language consisting of strings which are Turing machines with inputs. So M alpha halts on X and outputs a bit. Okay, so these are the, as halt suggests, name suggests, these are Turing machines with inputs on which they halt and give an answer.